This week in lab we are doing the dehydration of 2-methyl-2-butanol. Let's take a look at our mechanism for the reaction. First step of the mechanism, anytime we see a strong acid, look for something to protonate. What do we have that can go and get the proton off of the strong acid? It's the lone pair on the oxygen. So this first step is just an acid-base reaction. We also have HSO4 minus out here. Now that's a poor nucleophile, so this can't do anything. Busy doing resonance. So the only option for us here is for the water to leave off on its own to give the carbocation. Ahead and drew some hydrogens out so we can see the next step take place. The water that left is going to act as a base and grab a beta hydrogen. Alpha is where the cation is. The next position out's beta. We have beta here. We have beta for this methyl and a beta this methyl also. And I'll put those same color because they are equivalent. So it doesn't matter which one you go to. So the base could grab this beta hydrogen. Electrons kick toward the carbocation and form the alkene. There's the alkene that you get. The water acting as a base could grab one of these beta hydrogens, one of the blue ones. Electrons kick in toward the alpha position, form the double bond, and this is the alkene that you would get. Now let's examine the two. This alkene is tri-substituted, this one is di-substituted. We know we want the more substituted alkene. This will be our major product. This is Zeta's product, the other one is the Hoffman. And this will be the more substituted alkene will be the major product. This one here is just a minor product. You get about 10 or 11% of the minor. The rest of it's the major product. Let's look at a so there's the full mechanism. Let's look at a rate equation for this reaction. First step is an acid-base reaction. All acid-base reactions are extremely fast. The only thing that can beat an acid-base is radicals, and we haven't looked at radicals yet. So this is, for the moment, it's the fastest reaction that we have is an acid-base. Second step, having to wait for water to leave off all by itself, that's a very slow step. It's got no help. That's a slow step. Last step, water grabbing a beta hydrogen, that's another acid-base reaction. And again, that would be a very fast step. All acid-base reactions are very, very fast. So if you recall, our rate depends on the rate constant of the slowest step. So the rate of this reaction equals the rate constant over the slowest step. And I'm going to put that as K2. We'll call this one K1, this one K2, and this one K3. That's our 3 steps. So it's the rate constant of our second step times the concentration of the species involved. So what is involved? All that is involved is this protonated alcohol. We're just waiting for the water to leave off the protonated alcohol. So there's our rate equation. Rate equals rate constant times the concentration of the species involved. We only have one species involved in the rate determining step, our slow step. This is the rate determining step. So this mechanism that we put up here, we are doing an elimination, but it's an E1 mechanism. Rate only depends on the concentration of one species. So that's our reaction that we're doing this week. I want to show you another one just to remind you what we talked about in lecture. Since we are going through a carbocation intermediate, you always have to watch out for cation rearrangement. Now this one that we're doing this week, we form a tertiary carbocation, so it's not going to rearrange. But let's take a look at another one. So let's look at this one. So again, we're going to protonate the alcohol. Gives us a water molecule that is a good leaving group. It leaves off, gives the carbocation. That is a secondary carbocation. If we do a hydride shift, then it can get to a tertiary carbocation. We want to grab a beta hydrogen. We have alpha is where the cation is. We have beta here, those are equivalent. And we have a beta here. If we grab one of those red beta hydrogens, and this is the alkene that you would get. If you were to grab one off of the blue beta position, this is the alkene that we will get. Now let's look at which one would be the major product. If you look at these two, this one's tri-substituted, this one's tri-substituted. Both alkenes are tri-substituted. If it's a tie in substitution, substitution is the most important, but if you have a tie in substitution, you're more stable in the ring than you are outside the ring. So this one is the major product. This one would be a minor product. So watch for cation rearrangement. We can do hydride shifts and methyl shifts. So any of these carbocations, always watch for cation rearrangement. Let's take a look at our procedure here. Before I forget, let me talk about the post-lab questions. We are not going to be doing GC analysis in this lab, even though it's in the procedure. Our GC is currently not working, so we are not going to run GC. So I'm going to take out some questions here of the post-lab questions. Only answer question number 1 for your post-lab. Only question number 1. Don't do 2, 3, 4, 5. Just question number 1. On the procedure, we're taking 2 mils of water in a 5 mil long-necked, round-bottomed flask. So you got 2 flasks in your kit. One's got a short neck, one's got a long neck. Get the one that's long necked. We're adding in 1 mil of concentrated sulfuric acid. It says drop-wise. Notice that it says drop-wise. Don't just dump it in. You got to go slowly adding the acid. If you dump it in at once, it's going to start boiling and pop out on you, and you'll have acid all over you. So you add slowly to that water, drop-wise. Drop, drop, drop. Flick the tube during the mixing to mix it during the addition. So add a couple drops, flick the tube to mix it, add a couple more drops, flick the tube, mix, keep going until you've added all the sulfuric acid. You're going to cool that solution in an ice bath. Give it 5 minutes to cool well. Once it's cooled, you'll then add 2 milliliters of the 2-methyl to butanol. That's our starting material. The acid that we just added, that was just a catalyst. You get the acid back at the end, so it's acid catalyzed dehydration. Again, flick to mix it. You're going to add a boiling stone to the round bottom flask and set it up for a simple distillation. And you've done simple distillation in the past, so you should know how to set that up. The receiving flask that you're going to be collecting the product in, you need to make certain you cool that receiving flask. Our products are extremely volatile this week, and if that vial that you're collecting into is not cooled, you will lose everything. So make certain that vial that you collect into is being cooled. You're going to begin the distillation by slowly heating on the sand bath. The product should distill between 30 and 45 degrees Celsius. You'll stop once the distillation really decreases. It will start slowing up there toward the end when it's finished. Turn off the sand bath light to cool, and then we're going to do some washing. Now we're adding 0.6 mils of 3 molar sodium hydroxide to the distillate. That's just in case any acid happened to distill over. So sodium hydroxide being a base, that would react with any acid that may have distilled over. Mix it well. You can do that by flicking the vial. And then you're going to draw off the lower layer. That's the water layer. Organic layer will be on top. So take a pasteur pipette, draw off that lower layer. Once you've done that, get that vial back in the ice. Keep our products are extremely volatile this week, as I already mentioned there. So keep your vial in the ice as much as possible. Use a lid on the vial, the cap, screw cap. So keep everything in ice as much as possible and keep the cap on as much as possible. Now, I know you have to take it off to be able to draw off the lower layer, but try to keep everything in ice and keep it as cold as possible. Now, once you've removed the water layer, you'll dry it over anhydrous calcium chloride pellets, the organic layer. And while that's drying, you're going to clean your distillation apparatus. We're going to distill a second time to purify the products. and it goes through and it tells you how to clean out everything. We'll set it up and do a second distillation. Distill it a second time, so transfer the dry mixture after we've dried it with calcium chloride pellets back to the distillation flask, and we'll add a boiling chip and distill again. And you'll collect the portion that boils up to 43 degrees. Don't go above that. Now, this time pre-weigh your vial that you're collecting into. Pre-weigh it before you set everything up. Get a weight of it empty, because we're going to be calculating a percent yield. So we will distill up to 43 degrees, and then you will, once that's finished, you'll take and weigh the product, and you can subtract the weights of the vial then and get the weight of that product, because you have the weight of the empty vial. And you will calculate a percent yield. A typical yield, it says, should be about 50%. That's what an average student will get. Maybe you will get better. Maybe you don't quite get 50%. That's just what a typical student will get, is 50% on this reaction. Now, this is the first time this semester that we've done a percent yield. All the previous labs we did a percent recovery. Percent recovery is where we purified the material, but we got the same material back that we started with. It's just more pure. That's a percent recovery. Percent yield is when you make a new compound. So here we're taking an alcohol and making an alkene. We're making a new compound. So you have to do a percent yield. Now I'm going to show you percent yield. This is the one and only time I will show you. From here on out, rest of Organic 1 and in Organic 2, we will be doing percent yields, not percent recoveries. Percent yield is actual over theoretical times 100%. Now let's talk about the theoretical yield. We only have the one reagent this week, the 2-methyl-2-butanol. Sulfuric acid is just a catalyst, so you get the same amount back as what we started with. So that's not a reagent, it's a catalyst. If we have more than one reagent, you will have to calculate the limiting reagent, the one that's in the least amount as far as moles go, and then use that one to calculate your theoretical. But we only have the one reagent this week, so we don't have to do a limiting reagent. We only have the one. But again, if you have two reagents that we're adding together, or three or whatever, you will have to calculate all of those and see which one is in the least amount, and that is the limiting reagent. That's the one you'll use. Now we're starting with 2 mils of the alcohol. We need to get that into grams, so we'll use density. The density of 2-methyl-2-butanol is 0.815 grams per milliliter. That's the density of the alcohol. So you can see our milliliters cancel out. So we're just multiplying by the density. Now we want that grams in moles. So a mole of the alcohol, we'll use molecular weight here. 88.15 grams per mole is the molecular weight. Now we need to flip that, put it on the bottom so that our grams cancel out. This is just the molecular weight of the alcohol. You can see our grams cancel out. Now, if you notice in the reaction, we get 1 mole of product for every 1 mole of alcohol. It's a 1-to-1 ratio. Not always the case. Now we'll go ahead and put it in here, but it's not always the case. Sometimes you have, a reaction, say 2, I'll use a generic A here, maybe 2 A's go to 1 B, something like that. But today, our reaction, 1 of the alcohol is giving us 1 of the product. Now, our moles of alcohol cancel out. Now we have moles of product. Let's go ahead and get it into grams of product. So we'll use the molecular weight of our product, of our alkene. And the molecular weight of the product is 70.13 grams per mole. That's the molecular weight. Now, if we multiply all that, that gives us our theoretical yield. 1.3 grams of product is our theoretical yield. Now, since the GC is not working, I want you to run some instrument. So we are going to take an IR spectra of your product. Now again, your product is extremely volatile. Please keep the cap on as much as possible and keep it in the ice as much as possible. So got a beaker of ice, you got your vial in the ice, take the whole beaker and everything with you down to the IR room. You'll take a spectra of it and you will talk about that spectrum in your conclusions. I'm going to give you a spectrum of the starting material, the starting alcohol, and you'll have the spectrum of your product. And I want you to talk about how those IR spectra show that we converted the alcohol into the alkene. You can talk about peaks disappearing and or peaks appearing. Now when you talk about the peak, so if you look at our reaction, the alcohol should go away. We're converting the alcohol into an alkene. So an alcohol should have an OH stretch, and the OH stretch is this week. I'll give you the spectra when you come to lab. I have it here, and it says it's at 3369 reciprocal centimeters. So in your conclusions, again, talk about the spectra. So you can say, the OH stretch at 3369. Give me the position. Don't just say OH stretch. I don't know which peak you're talking about. Say the OH stretch at 3369 reciprocal centimeters. Don't forget the units. Disappeared. Hopefully it did. We'll be able to see in your spectra, in your product, if it did all disappear. They might still be a little bit in there. And we'll know if your reaction didn't go to completion. So that disappeared. You should see sp2CH stretching appearing because we're making an alkene. And you should also see a carbon-carbon double bond stretch. That should be appearing. So talk about those, where they're located. So that's how you discuss an IR spectra in your conclusions. Remember the carbon-carbon double bond stretch. That's down about 1620 to about 1680 reciprocal centimeters. Usually pretty small.